Hi, welcome back to this continuation of this video series about material phenomena in nuclear environments. So firstly, we want to discuss what the solid fission products do. Okay, remember that there are 6 groups that we have discussed before. Okay, one is the group 1s, one is the group 2s. Okay, so this is 1, 2, 3, 4, 5 and 6. So these two are usually in the gaseous phase. This one is it depends on where it is. If it's in the center, it can be acting as a gas. At the outside, it's more like a solid. All these here, these are solid phases. So we want to discuss the behavior of all these. Okay, 1, 2, 3, 4. Okay. So how does making new solid products, how do new solid products affect thermal conductivity and swelling? Previously, we've discussed before that Frankel pairs can cause swelling, the pKa cascades can cause swelling, and of course fission gas that can cause swelling. But can solid products cause swelling, and how does their thermal conductivity affect it? Well, let's talk about thermal conductivity first. If you talk about metallic inclusions, that like the noble metals, these will have a better thermal conductivity. And each oxide, each of the different oxide phases, like the Alkali Earth oxide and everything, okay, so thermal conductivity, so the metals will increase, the metallic inclusions, metal inclusion, this will increase the thermal conductivity, but there are different oxides as well. So we have the lanthanides that are generated. We also have the lanthanides, plutonium. We have what else? Alkali Earth oxide. And the alkali metals. Alkali metal oxide. Excuse me, yeah. So each of these have a very differing effect on the thermal conductivity. However, the effect could be considered small. So this is small compared to the loss in thermal conductivity due to fission gas and neutron induced swelling. So okay, when you generate new lanthanides, new alkaline earth oxides and new alkali metal oxides, these will cause differing effects on the thermal conductivity. So if the thermal conductivity for this alkaline earth oxide is higher, for example, you expect the thermal conductivity of the fuel, which is generating this, to be higher. So if these alkaline earth oxides are present in the fuel and they are being created and put into the fuel by the fission process, and this conductivity is higher, then the conductivity of the fuel is higher. But we have many of these different elements being made with different conductivity, so there will be a range of things that can happen. So the overall can either increase or decrease, but it may not be so important because the fission gas and the neutron-induced swelling, this will lower the conductivity way more than whatever changes you are producing here. So that settles it. It's not as important to think about. Now, how about swelling? How about swelling? So do solid fission products, does it affect the swelling process? Now we will have to consider the individual volumes of each of these solid phases. So that means including, we want to take into account the densities of each phase. So we, in this consideration, we also include cesium, since that is solid inside the fuel for the most part as well, except in the center. So include cesium as solid. So in the beginning, before fission, so the volume of UO2, so this is the volume of the fuel, is equals to number of UO2 atoms times volume of the UO2 atoms. Okay, so I will just write this as Nu times omega U. Okay, so these are the shorthand forms I use. This is a volume, this is volume per UO2 atom. This is the number of UO2 atom. So if volume per UO2 atom times the number of UO2 atoms, that will give you the total volume. So, but we also have to consider during fission. So we want to measure the volume change, okay, before fission and during fission, or this is also the after, if you want to call it before and after. You want to measure volume change. So there are some terms we want to use. This is a term called burn up. This is burn up. You may have heard of it before, but if not, it's just a measure of the fraction of the fuel that has been used. So this is the fission rate times the time. So this is the total number of fissions happening over the number of uranium atoms. So this includes 238 and 235, not just 235. So this burn up, it refers to the fraction of uranium consumed. Okay, so after fission, we can represent the volume as such. So this will be equal to the volume of UO2 atoms plus volume of fission product. Okay, so we have to consider that some of the UO2 atoms have been consumed in the fission reaction. So this will be omega U times Nu into, well, we have to think of the fraction of uranium that has not been consumed yet. So that is 1 minus beta. Okay, and then how much of the excuse me, how much of the what do you call it, fission products are produced? So this will be beta into omega of the fission products times the number of atoms of the fission products. But hey, there's more than one fission product, right? You cannot just use this omega and then this number of fission products or number of atom of fission products to kind of measure. We have to account for each group that is being formed. 1, 2, 3, 4. 4 groups. So let's look at the second term. Okay. So we can rewrite this as follows. Beta into Y, the yield of the fission product. So let's say this is the lanthanides group times the volume of that fission product group times the number of that. Okay, forget the yield first. So it's the volume of that fission product group plus the number of atoms in that fission product group. So there'll be metal inclusions as well. Then we include all the other groups. Okay, so this we can write as summation of the fission products of the various groups. So we sum all these up together. Okay, now how can we write this? This is the number of atoms. Okay, number of atoms of a fission product group. Okay, how can we write this? We can write it as the yield of the fission product group times the number of uranium atoms being consumed. Okay, actually the burnup should not be here at all. This is how we consider it first. Sorry, there should not be a burnup. So this is the number of uranium atoms being left over. This is the number of fission products being generated. Okay, so this should make the sense. It's just this summation now that we want to consider. Alright. So if we want to talk about this Ni, this can be substituted by the yield multiplied by the number of uranium atoms that are being consumed. Consumed or fission. So this is the number of uranium atoms being consumed or fission, and multiply that into the yield here, and that will give you Ni. So this expression can also be written as summation of omega I, Yi, and U beta. So this is the burnup times the number of uranium atoms times the yield of that particular group. The yield of that particular group times the volume per atom of that particular group. Now this is independent of any group, so you can factor it out. Okay, so what is our final volume expression? Our final volume expression will look something like this. Final volume equals to omega U and U 1 minus beta plus NU beta sigma of omega I into yi. Okay, so remember our initial volume, and that is equals to omega u and u. So this is the number of uranium atoms to start with. So if we want to find a swelling equation, all we want is this delta V by V. Here, if you just use, just find it for the solid fission products. So we have a V final minus V initial over V initial. Okay, so what is the V final? It's over here. This is the V initial. So what we want to do is just substitute in omega u and u. Okay, over, and then V final is here, omega u and u is beta plus nu beta sigma omega I yi minus omega u and u. Okay, now we'll notice one thing, this will cancel out with this. So 1 times omega u and u will cancel out with this. So let's cancel. What we are left with is nu beta sigma omega I yi minus beta omega u and u, where omega u and u. Okay, and now we just divide throughout by nu, because that cancels out. Beta sigma omega I yi is beta omega u over omega u. So now we want to divide throughout by omega u as well. Okay, omega u. So let's write that in the next part. Beta sigma omega I over omega u I is beta. Okay, so now we just factorize the beta out. Sigma omega I omega u yi minus 1. So that is the formula we have derived. Now you just want to take some typical values to find out how much swelling there is. And here are some typical values from chapter 12. Again, chapter 12 of Professor Olander's book. So, in the soluble, we have a certain value of yi and certain value of omega I over omega u. So this soluble in the fuel, these are the lanthanides and the actinides. So we can do a table as such, and this is the table being presented in the book. 0.683, 1.00, 0.683. So metallic inclusion, this will be 0.503, 0.36. This is from the textbook, and here is 0.181. Okay, alkaline earth zirconiates. So this is the group 2 section. 149, 1.74, 0.258. 0.258. Okay. Now we look at the cesium and rubidium. So this is the kind of a gas, but not quite the gas. Cesium, rubidium, iodine, beryllium. Okay, 0.238. Okay, so there is an others group as well. For everything else that doesn't quite fit these groups, but these are quite minor. So other FP. Okay, sometimes you include this group as well. So they're everything else that doesn't classify into the 6 groups that we have mentioned. So the total 324. This is the total, and this is this term over here. So beta 1.324 minus 1 equal 0.324 beta. Okay. So per atom percent burn up, there is 0.324% swelling. So remember, this is delta V over V. So you see, solid products can cause the fuel to swell. So now with solids out of the way, let's move on to discuss a little bit about fission gases. Thanks for watching. I'll see you guys next time. Bye bye.